Can I share my screen?
Yeah, I hope so. Can somebody arrange that? Yes, it works.
See it? Okay. Now I have to get it to the PowerPoint.
Yeah, you click that. Yeah, that
Okay.
should work. Perfect.
Well, whenever an ancient person is invited to give the last talk at a conference, it usually means that he's supposed to summarize the conference and sprinkle it with his little bits of wisdom and perspective and so on. Well, I hope that's not what the organizers wanted from me, because I don't have much wisdom anyway, but I plan to talk about my some research we've been doing, and I will come back to a little bit to the conference at the end of my talk, though. So what I really want to talk about in this talk is this business about imaging with coherent GISAXS. This has always been, we've had the DWBA around for a long time, almost ever since I started coming to SXNS meetings, in SXNS 2, actually, in Bad Honnef. Since that time, DWBA has featured, and GISAXS and GSANS have featured prominently. And I say coherent GISAXS, and I'm afraid I can't say coherent. I would love to say coherent GSANS, but unfortunately there is no such thing. And so this will be basically something you can do with X-rays. So I've always thought it would be wonderful to be able to actually, it's nice to do SANS, SANS, and so forth, but it'd be nice to be able to put things on a liquid surface or on a solid surface or on an opaque substrate where you can't go through it and actually image that, get a real space image of that. And the thing that stops one doing that is the complications introduced by the DWBA, which need to be addressed. And that's what I'll try and talk about here. So first of all, let me give my acknowledgements where they are due. We've had a lot of very helpful interactions with Zhang Jiang and Jin Wang at Argonne at the APS, and they've been very helpful. And John Miao at UCLA has also been very helpful, and I've had several helpful discussions with him. But I really want to thank my student and co-author, Yi Yang, who I will just take a minute to tell you he's actually a remarkable person. He joined my group as an experimentalist to go to synchrotrons and do experiments, and was doing so very well until in a skiing accident, he fractured his spine and is paralyzed permanently from the waist down and is in a wheelchair. And when that happened, I wondered how we would continue, but he told me that he absolutely wanted to continue with getting a PhD. And so I thought, I said, okay, I'll think of a sort of a computer-like project for you where you don't have to go travel to synchrotrons. And I came up with this thing that I'd been thinking about for a long time. And he did a really fantastic job on it. He's a remarkable guy. So let me go on. Let me see. So as you probably know already, GISAXS and GSANS can be used to study structures and phase transitions in polymer films, magnetic structures and thin films, quantum dots, nanoparticles on films, on surfaces, semiconductor nanostructures, integrated circuits, supported catalysts and magnetic storage materials. Here's some pictures of magnetic domains on the surface of a material. Here are some ordered nanoparticles and the GISAXS pattern. And here is a block copolymer, which sort of goes into this shape when it phase separates, and so forth. So we know that over the last 20, 30, 40 years, these kinds of things have been studied and studied very well, and it's become an exponentially increasing field where there are lots and lots of instruments in all the synchrotron and neutron sources devoted to doing these kinds of experiments. I can't seem to. Other applications would be computer chips, for instance. That would be great if you could actually image these, because I think the computer industry would be extremely interested in that. And now, very recently, there was a paper by Gabe Epley's group in Switzerland, where they did basically a Tycho tomography of a computer chip, and that was a tour de force, and it made a huge hit in the popular literature and in the newspapers or whatever, because industry was very interested. But by and large, the current uses of GISAXS and GSANS, so that was not actually scattering, that was tomography. The current uses of GISAXS and GSANS and DWBA to go with it, they often, these experiments are often used to just obtain broad features of the sample structure without a detailed analysis. You can get a lot out of just looking at the grazing incidence scattering pattern, in plane ordering, the orientations of molecules on the surface, and so on. This has all been done, and then no detailed analysis was required for that, at least not really detailed analysis. The structures studied are usually quasi two-dimensional, and detailed analysis has involved usually models, as we've already heard in several talks at this conference. Models often using DWBA fitted to the data, and there's commercial software to do this, I guess, Born Again and other programs. And the LBNL group in Berkeley is developing a series of codes that people can use to recognize patterns from different kinds of shapes, three-dimensional shapes, to try and see what their GISAXS is telling them. I think ultimately, as has already been mentioned, these kinds of pattern recognitions and GISAXS patterns and so forth will be enhanced and rapidly soon with the use of artificial intelligence and machine learning. Now, let's talk about phase retrieval imaging in transmission geometry. This is a conventional phase retrieval imaging that's been around now for the last, well, almost 20 years, but it's been quite big for the last 10 years. Basically, it's a technique that was developed by the people in optics, and it was then taken up by the X-ray people, and David Sayers, I believe, was the first person to suggest that if you didn't have to, I mean, everybody knows that you can solve crystal structures if you've got a crystal lattice and some other tricks to get the phase, to solve the phase problem. But if you don't have a crystalline object and no Bragg peaks, and you don't know the phase, then how do you get information about the object? Well, you do this thing called phase retrieval imaging. And what here's a geometry of this thing, where the beam comes in. It's like a small angle scattering experiment, basically with a two-dimensional detector. And they use what's called, basically this thing called the Gershberg-Saxton algorithm. So what you do is, the basic idea is this: you measure the intensity of the speckle pattern. If it's a coherent, it has to be a coherent beam, otherwise this thing won't work. So you have with the development of the, the brilliant coherent sources in X-rays, this became possible. And now with even more, I mean, like Max 4, presumably, and following Max 4, all the other synchrotrons like APS and ALS and so forth are also trying to upgrade to higher brilliance using this multi-band achromat mirrors and so forth. So so the idea is basically you measure the intensity, which is the absolute magnitude of f of q. It has a phase with it, and if you could, so this is the scattering amplitude, and it has a phase phi naught of q. You measure it q by q. If you could measure the phase and invert it, you'd get the electron density of the object, and you'd have the image. But you don't know the phase. So what you do is, for every q, you guess a phase randomly. And then you Fourier transform it back to get a real space fictitious electron density. And then you make sure that this electron density satisfies certain conditions. You put it to 0 if it goes outside the frame of the image. You put it to 0 if it becomes negative or complex. In other words, it has to be real and positive and within the frame of the image. And you can choose a thing where you mix in a little bit of the last iteration, and with a parameter beta, which you can adjust, and then you keep going. You then, once you've done that, you've got a new so-called electron density. And what you do is then you have the Fourier transform of that, which has got a phase. You divide by the observed magnitude of the intensity, and that gives you the phase. And then you recycle. Now you put that phase in and you keep going round and round in this loop. And eventually, amazingly, almost by magic, usually these things converge and give you a real space electron density, which is amazingly accurate and down to the 10 nanometer scale or so. So this is also known as lensless imaging, because you don't use any lens or any focuser. You just use basically the speckle pattern, that's the scattering pattern. And this was the way it was, the first sort of experiments of this type were done by John Miao and David Sayre and some others, where they put a pattern of gold dots. This is an electron microscope image. They got scattering from it, which looks pretty, I mean, it doesn't look like it has much information, but when they went through this algorithm and inverted it, they got something that was remarkably like the original image. So the method worked. And then in grazing incidents, Jin Wang's group at Argonne and Zhang Zhang, they took the Argonne logo, and they had to, since they were doing it in grazing incidents, they had to make it extremely long in one direction, like 40 times longer than the other direction. So it's a very distorted Argon logo. But they then got a scattering pattern with speckles from the APS, and they went through this thing and they got the logo. Now, all of these basically assume more or less that the image, that the scattering pattern is basically the Fourier transform of the object. And so the thing that I told you before works for this, and it even worked for that, even though this is grazing incidence, and you'd expect the reflected beam to give rise to a problem, but apparently it didn't here. So in some cases, it doesn't, I guess, and we've seen that in the literature also. There have been, for instance, there's also this question called the thing called oversampling, which means that you actually have to make sure that you've got enough Q points to make up for the lack of phase information. So you actually, if you measured the intensity at n points, you need to measure at 2 endpoints to get the phase as well. You got the amplitude, you got n amplitudes, but you don't have n phases. And that's sort of done by taking this image, for instance, which has this Fourier transform, and then just putting it in a frame and taking zeros outside and taking the Fourier transform of this whole thing, which is now a 512 by 512 Fourier transform. I'm talking about discrete Fourier transforms here, and getting this Fourier transform, and that's what oversampling is. And so that's fairly easy to do. If you want now, all of these things have basically worked for things that are basically two-dimensional or flat. And you'll see there's a reason for this when we discuss the DWBA, because you know, the things that even the DWBA, if it's a two-dimensional thing, you don't need DWBA. It's just a Born approximation and just a Fourier transform that is there. So if you wanted to do using the Born approximation a 3D object, you can do tricks like this. You can tilt the sample and go through it at excuse me, different angles. Or you can and you can build up the image as a three-dimensional Fourier pattern in three-dimensional Fourier space, and then Fourier transform back. But that it's like basically it's like tomography, and it probably takes a great deal of time. Although I think this has been done by Chapman and his group and John Miao and his group. Now, as you all know, we've seen this before in Professor Bushbaum's talk, that the scattering amplitude, I'm talking about the amplitude now, in the DWBA is made up of 4 terms. And they correspond to these processes that have already been discussed. One of those, at least one of those processes involves scattering off the substrate. And it's these processes that mess up, this would be the simple Born approximation. Single scattering from the sample gives you the Fourier transform. But these processes give you extra speckle or destructively interfere with these and mess you up. And that's why DWBA becomes important, particularly when you're close to the critical angle. And so what you have now is not the Fourier transform of the object, but the sum of 4 Fourier transforms, each involving the same QX and QY, but four different QZs. And they are given by these expressions here, down here, KF minus KI, which is the ordinary Q, the negative of that, and then kf plus ki and the negative of that. So two of them are positive and two of them are negative. And that's an interesting thing to note, because when you do a GISAXS experiment, you don't normally measure negative QZ because it's below the horizon. But if you do DWBA, if you do GISAXS, you'll see that those negative Qs are actually there and contributing. And the other thing is that if the things are two-dimensional, then the QZs don't matter. They're not part of the Fourier transform, and it goes back to the ordinary Born approximation. So 2 dimensions is trivial. And the DWBA has nothing to say about the QX, QY part. That can be, you know, you can get that. Well, I should take that back, because these interference processes could affect that. And then the intensity is the modulus squared of the sum of these 4 terms. So again, you don't have the phase of this amplitude. And you need actually the phase of all these components, because this is the Fourier transform of the actual electron density. You need the phase of this thing and then be able to have it at all Q points and Fourier transform it back. And that's and these coefficients are given in terms of the Fresnel coefficients for transmission and reflection at the interfaces. Now, this algorithm is just, what we do is just generalize the algorithm that was used for the Born approximation. We measure this quantity, which is the magnitude of G of Q. That's what we actually measure, the measured intensity in the DWBA GISAXS pattern. And for each Q, again, you go ahead and guess the phi, okay? And then when you guess the phi, you've got essentially a linear combination of 4 different Fourier transforms of the electron density. And you think that you don't have enough information, but you do if you actually note that over the area detector, all the different QZs are there, as well as if you tilt the incident angle and have a range of incident angles and a range of combinations of KF and KFI and KZI and KZF, you actually have enough information to solve these equations. I won't go through the details of how those equations are solved, but you actually have more than enough information, so the system is overdetermined, and you can set up this matrix A, which is defined later on, but I won't go into it in detail, and is known as the least squared method to solve an overdetermined set of linear equations. And in terms of this, you can actually then solve for the individual Fourier transform, F and Q, which is the actual Fourier transform of the object, in terms of all these, all the measured values of the DWBA intensity in the GISAXS pattern. And then you do you Fourier transform back, and you go through the usual cycle, and eventually it'll converge, and it'll converge to the real object. How are we doing on time? I'm not sure what the time is, because I don't.
There is about 4 minutes left.
4 minutes?
4 minutes. 4
Okay.
minutes.
All right, so I'm going to skip the details of the mathematics here, which is just the process of solving the equations for these 4 Fourier transforms in terms of all the measured intensities on the area detector and for the different angles of incidence. And and one of the things that you do is you use Friedel's law, which says that when you've got an f of qx, qy, qz, it's the complex conjugate of f minus qx minus qy minus qz. You utilize that in the mathematics too, because that says that the density is real, basically. That's all it says. And then I want to show you some results. So we took a bunch of objects that are different shapes and different heights and put them on a silicon surface. And we assumed they were made of gold, so they were good scatterers. And this is the GISAXS geometry. This is all simulation. We simulated the scattering using a photon energy of 8 kilovolts with angles of incidence from 0.03 degrees to 0.63 degrees. And we used the DWBA to calculate the scattering pattern because we assume that the scattering is more accurately DWBA than anything else. That's optimistic in some cases, I know, but. And then we rotated the sample with 500 azimuthal rotations and 32 incident angle, outgoing angle, 32 KI-KF pairs to give you a total of 500 times 32 scattering patterns. Now that's as many patterns as you'd measure if you did tomography, actually. But a GISAXS pattern can be taken very quickly at, in some cases, just a second or two. So this may not be impractical, and there may be more efficient ways to cut these numbers down and still not lose the detail we need from the image. But anyway, you can see it works very well. This is the actual objects projected in the XY plane, the XZ plane, and the YZ plane. And this is the reconstructions. And you can see that the brightness corresponds to the scattering intensities from these objects, but you can see that it's very good. The only thing that has changed is that there's an overall random shift to the left or the right of this pattern because a translation of the whole object, keeping the relative distances the same, does not change a scattering pattern, right? We all know that. And so this is what the speckle pattern looks like. And here's a more three-dimensional rendering of the object that we're imaging. So this is a real three-dimensional system, random system, and we are trying to image that with coherent GISAXS. And here's the phase retrieval method. You see it does very well, actually, for this. And then here are some more simulations with random spheres. Again, they look pretty good. Then we want to say, can we reconstruct internal structure objects? So we put a cube of rather lower electron density inside a sphere with the ends of the sphere chopped off. And this is the reconstruction, this is the object, this is the reconstruction, this is the object. So it looks pretty good. So the conclusion is that successful phase retrieval for three-dimensional diffraction pattern and reflection geometry has been, it's now we've shown it can be done a simulation. The real thing is to do an experiment, and then there, of course, going to be undoubtedly many difficulties. Whether there going to be enough intensity, you want the footprint to essentially completely, you want the sample to rotate inside the footprint and not go in and out, although maybe one can develop a tachography way of doing this. So this footprint is very anisotropic, and it makes it a little awkward to rotate a sample and keep it inside the footprint. And also the question is, when you rotate, the question is, do you move the sample? What is the sphere of confusion and so forth? Those issues have to be resolved. And if that's the case, then you have to realign for each rotation angle and incident angle. That would be too much. So we hope that stages can be made where you get the desired accuracy. All right, so that actually is what I wanted to say in this talk. But I wanted to end by saying that I really think, since I'm the last speaker, that I ought to thank Tom Arnold and his committee, very competent committee, for having had the fortitude to cancel 2020, cancel 2021, and still have this meeting in spite of all the difficulties. And I think it's definitely been worth it. They've had to do an enormous amount of work, and we've probably lost a lot of people who couldn't make it or decided not to make it. I think we would have had probably even a bigger conference, but we've had a really stellar group of people here. I'm glad to see many of my old friends here, although many old friends are also missing. I think that we ought to give them a very sincere vote of thanks for all the. So turn your sound on and let's give them a sound applause. Okay. You did a great job. So thank you. And since this is probably, if you'll indulge me, since this is probably my, in view of my advanced years, since it's probably my last SXNS meeting, let me say that I want to, it's really been, it's been so nice seeing many old friends. I appreciate through the years, all the years of SXNS, knowing all of you and interacting, and it's really, it's been wonderful. And the people who worked with me, my postdocs and my students, from people way back like Milan, Sanyal, and Hanjung Kim, and my colleagues who worked with me like Ben Arco at Brookhaven, and my students like Yi Yang and others. I have to say that I'm very grateful to them, because without them, I wouldn't have been able to do anything. So thank you very much, and I'm very appreciative for all the help and friendship I've got from this community over the years. Thank you.
Thank you very